Hello and welcome to week 11 in artificial intelligence. This week we're going to be talking about deep learning, one of the more popular topics in artificial intelligence these days. So we'll start off with a discussion of the assignments that are upcoming, and then we'll move on to chapter 21, which centers on deep learning. So first, the assignments. We are into week 11, so this week you should be turning in your paper, which centers on deep learning frameworks. Looking ahead, you'll probably want to start on your project in week 12, which deals with learning. And then week 14 centers on another project that deals with natural language processing. You may also find yourself utilizing a deep learning framework when you do your natural language processing. That's entirely up to you, but you do want to do something interesting with it. And then your final paper is on robotic simulations. That's due at the end of week 15. As always, if you have any questions about these topics, reach out to me. That's what I'm here for. But again, remember to do your submissions for your ideas on your projects sooner than later so that there's time for me to respond to them and to give you direction and also time for you to implement them. So do plan accordingly. More detail on the paper related to deep learning frameworks. Research deep learning frameworks. Start with chapter 21 in the text. Describe the goal and purpose of a deep learning framework. Define all the key terms associated with those frameworks. Then research two frameworks. You might want to use something like PyTorch, TensorFlow, etc. Describe and compare the frameworks. So give a brief background of where they came from. What are they used for? Any sort of things that are descriptive about them and potentially how they differentiate between each other. You're going to need at least 4 scholarly sources, and you do want to utilize APA 7th edition formatting and style. I would expect you'll come in around 1,500 to 2,500 words, though it's hard to say with certainty. Your paper will be graded using the same rubric that is used in all the courses writing assignments. Be sure to shoot for that excellent column, and that all starts with having a strong thesis statement and a list of your subtopics. When you have those things, that piece of information shows up in your introduction and in your conclusion. In the introduction, you're saying what you're going to say. In the conclusion, you say what you said, and you show how you did what you said you were going to do. Along the way, you're going to use the thesis topic or the thesis statement and the subtopics to both build that argument or to walk through the process that you say you're going to walk through. That's going to speak to things like focusing and sequencing and support. You're going to use citations to support your claims. You do want to make sure they're peer reviewed as much as possible. In this situation, you do want to find 4 peer reviewed papers to use as sources. In addition to that, you likely will include sources related to a particular framework, so perhaps the website where it can be located at. But understand that a website for PyTorch is not a scholarly source, so you need to find papers that have talked about it, perhaps the approaches that are utilized in the Torch framework or whatever it might be. The discussion for week 11 is similar to the ones that you've seen in the past. Talk about something that's related to this week's reading and describe it in a real world setting using your own words, trying to make it concrete, real, and tangible. So pick something that relates and tie it to something you have seen. As always, the use of resources of this course center on things associated with the text, including the text, the code that's included in the text, various implementations of the pseudocode in various languages, including Python. So you may want to take a look at that, especially when we talk about some of the deep learning stuff. Moving into chapter 21, which centers again on deep learning. So before we can get into what deep learning is, we need to talk about what like neural networks are. So we start with a simple feed forward network, then we'll kind of drill in on that over time. So we start off with some pretty basic things like where did it come from? And the concepts of neural networks are coming from a biologically inspired pattern. Now that pattern, our initial understanding of it was a bit off at the time we started using neural networks or trying to create them based upon how we thought the brain worked and neurons in particular. but it is inspired by it, and it does kind of attempt in some ways to mimic what we think happens. The reality, a little more complex than what we might have created, but it is where it came from. And the details are kind of irrelevant to some extent. So you can think of it as a gross oversimplification of a real neuron is this idea of a unit. And you can think of it as a kind of a squash linear function. And your idea is you have things coming in, you have some weights, you have a signal coming in, and you make a determination based upon the weights and the signal, and you get some sort of an output, right? So there's what's called an activation function, which is going to determine when, to some extent, the neuron fires, simplistically speaking. It's a gross oversimplification, but it kind of adds some idea of what networks of simple units can do, and that's kind of the takeaway. Activation function is something that determines when something goes from being off to on. Literally, that's what it comes down to. Most of the time, it's a sigmoid type function, and you can adjust the bias weights to move the threshold. Is the basic idea as well. So you can make it to where it'll tune itself. You don't do this itself because there's a bunch of these, right? So when we talk about it of a basic unit, how powerful is it? Well, it can do pretty much any logical Boolean function that we're interested in some fashion. So relatively expressive. And a simple feed forward network. So the basic idea is you take these units, you hook them together in multiple layers. And so those are key words here I'm saying. Layers is part of what you get the concept of being deep. When we talk about deep learning, we talk about more than one hidden layer. So there's typically, in most neural networks, essentially you've got an input layer and an output layer. In between is a layer that does kind of the work. In this case, there's a single layer, right? So this is a relatively, or is a very simple network example. And it's a feed forward network in the sense that things only go one direction. They go from input to output. So it's not something that like errors are propagated in some other direction. And the granddaddy of all simple single layer feed forward networks is the perceptron. I'm not going to go into it in a ton of depth, but you need to know it existed. It was an algorithm that was used and very popular for quite a while, and it adjusts the weights essentially, and so you're basically changing the shape of the function is how you can think of it. Pretty expressive. It can represent and or not, but not XOR. So it can do most stuff, but not XOR. So pretty useful. But also you can say they're the date, not necessarily new discoveries, right? Back in '69, so been around for quite a while. So we're going to move into the next phase, which is talking about computational graphs for deep learning. That's the next section in the text. Also makes sense for the next thing for us to talk about. So to do that, we're going to first go over the key terms and concepts, and then we'll go from there. So we need to start by, well, what is a computational or a computation graph? And it's basically kind of like the name said, it's a way of representing operations. And it is a graph in the sense that there's nodes and edges. Input encoding is getting data from raw form, how it's coming in. It's something that's usable. Sometimes it's straightforward, sometimes it's not. Sometimes when you think about things like images, it becomes a bit more complicated, right? Because an image is made up basically of a series of pixels. And I say here location, 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 because whenever you're talking about a pixel being on or off, simplistically, what's near it is important. And if you basically were to take an image and turn it into a long strip of dots, ignoring the position of each one of those units, you're going to lose a lot of the expressiveness of that bit, right? That pixel. So knowing where something is important, and so you have to do something kind of interesting in order to do that. So it's not as simple as just taking it and running it through as one big stream, right? It needs to be somehow encoded of where things are. We'll also use this concept of one hot encoding, and it's basically about a bit being turned on for each of the categorical values. So what this will do for you is let you do bitwise operations. So you'll move up in powers of 2 on the integer value of a category. But inside of the system, if you were to use something like a straight up integer as your category value, so 1, 2, 3, 4, 5 for different categories, 1 and 2 don't really have any relationship to each other. There's no value there. So a lot of times that's being done instead using something really simple to programmatically determine, which is if the bit's on or off. So each of the bit. So you'd actually move up in layers of 1, 2, 4, 8, and so on, 16, and so on. Hidden layers, as I alluded to briefly, are the layers that are not input or output. That's simple. So they're hidden in the sense that you don't interact with them. When you're using a neural network, you interact with the input and you get the output from the output layer. So that's kind of how those work. So what are computational graphs? Kind of need to know that before we can start talking about what they look like whenever you're doing this sort of stuff. So here's a graphical, it's essentially that. It's a graphical representation of a type of a calculation. So you have E equals to A plus B times B plus 1. You can turn those into, by introducing some artificial values, you can introduce C is equal to A and B, D is equal to B plus 1, and E is equal to C times D, right? And that's what this graph turns into. And these become pretty compelling because they allow you to think of them in different ways rather than just a series of instructions. And it's a form of expression parsing. This is something that's not just limited, certainly, to AI. It's a way of representing things in a more structured way. And it is a descriptive language of deep learning models. So that is a key concept to understand. It's also a functional description of the required computation and can be instantiated in at least 2 types of computation, forward computation and backwards computation. So whenever you look at this, you've got an edge. It represents essentially a function argument, and also its dependencies, and they're just pointers to nodes. A node with an incoming edge is a function of that edge's tail node, and a node knows knows how to compute its value and the value of its derivatives with respect to each other with each argument, edge, times a derivative of an arbitrary input. So that's kind of at a high level computational graphs. When you start looking at a forward propagation graph, it looks something like this. And again, we're not going to drain these sort of things, but it's important to understand kind of the foundations. Moving on to convolutional networks, and this is when neural networks really got interesting. So jumping again to concepts and terms, what is a convolutional networks? And usually they go by CNN, convolutional neural network, right? And it contains the locations of connections, at least in early layers. So in early layers of the neural network, it at least knows where things are. There's this concept of a kernel, which is a pattern of weights replicated across multiple local regions. And a convolution is when you take a kernel and you apply it to a pixel. Receptive field in CNN is the first unit in the first hidden layer. So right after the input layer, the very first layer after that is a unit inside of that. And a pool summarizes a set of adjacent units from a previous layer. A tensor is a multi-dimensional array of any dimension. And then we're moving on to what is a tensor. You have this concept of a GPU, graphical unit processing. Sometimes graphical unit processing units are used to run tensor processing units. There are also distinct things that are TPUs themselves. So we talked previously about what a typical kind of feed-forward neural networks look like. And this is actually would be considered a deep neural network on the left side because there are 2 hidden layers. There's not just one. If it was one, it wouldn't be necessarily considered deep, but when there's more than one, we'd call them deep. And that's for historical reasons. Comparing that to CNN, on the right side, you see that they're more viewed as being like a 3D representation. And that's because the actual value of a CNN is that it is able to determine that one pixel is next to another, which is really important whenever you're actually trying to do something like figure out what is the letters that are written on a piece of paper. For the next sort of type of neural network that you'll run across is a recurrent neural network. And so the key difference here is that a recurrent neural network, an RNN, allows for cycles in the computational graph. So that means that it can essentially loop, right, in some fashion. They have an internal state, which is a form of memory. There's a variation of types of recurrent neural networks called a long short-term memory, so LSTM, RNN. And basically the idea here is that you have memory cells that are copied from one time step to another time step, and it's usually controlled by some sort of a gating unit. There are the three different types of gating units are listed here on the slide. You have a forget gate, which basically does kind of what the name says, and it forgets the value. It doesn't move it forward. Input gate takes it from the previous, and then the output gate pushes it to the next. So the basic idea here is that these things will have ability to essentially have a memory, which is useful in certain circumstances. So when we talk about network structures, we've talked a little bit about them. You've got your feed-forward networks. Those are typically single-layer perceptrons, possibly multi-layer perceptrons, but the direction is always left to right, so to speak, input to output. Their feed-forward networks implement functions, but they don't really have any kind of internal state. They are, in that sense, stateless. Recurrent neural networks do have a certain amount of state through symmetric weights. So there's weights associated with them, and they do have a holographic associative memory in certain circumstances. And they typically have directed cycles with delays, and sometimes they have internal state that can oscillate like a flip-flop. So it can be on, they can be off. So here's a basic kind of view of a computational graph of a recurrent neural network at point of x at t, so x sub t sub 0 and so on. So x sub 0 is in this first one at t sub 1 and t sub 2 and t sub t basically. So that's the basic idea of getting it across, is that there is a relationship over time. And then a more complex kind of vision or version of a recurrent neural network's computational graph dealing with a many-to-many sort of relationship. So application, all kinds of them, right? So when we talk about deep learning, pretty much most of the field that we would talk about being artificial intelligence now is in some way related to deep networks. There are some exceptions. So there's some purely statistical machine or, algorithmic sort of approaches, but a lot of it is neural networks. We talk about vision, you get recognition like handwriting recognition. You've got potentially tracking and detection. You can't really have a self-driving car without some form of vision, and that's going to be most likely powered by some form of a neural network, probably a recurrent neural network. So also natural language processing, you've got translation, recognition. If you don't think that's important, how do you think Google, Alexa, and Siri are understanding what you're saying and then producing output? And also, you've got natural language processing, so you can be running something on your phone that translates real time or near real time from your native language to some other language in a reasonably accurate way, something that was very difficult to do previously. If it was easy, then why did R2D2 or C3PO have to be so big, right? Because that's basically what he did. Reinforcement learning, very powerful as well. It's what DeepMind and IBM used to win at Go. So much more complex than some of the other types of learning. So yes, very applicable and very useful. So this is a brief introduction of deep learning. The concepts are around connectionist approaches to learning, machine learning and such. Do spend some time reviewing the various frameworks so that you're able to do your paper. It's always a good idea to play with this stuff if you have time. If you have an Anaconda installation already set up, you can pretty much install most of the frameworks relatively easily. You don't necessarily have to have a GPU to use them in simple ways, though it'll be handy if you do, especially if you start using them in more powerful sort of situations. And with that, I will close. If you have any questions, reach out to me. That's what I'm here for. Stay safe, and we will speak again next week.